Morning.
Hey, good morning.
Let's see. Copy API token. Awesome. Let's see. I'm almost organized here. All right. We are tackling a little bit more about the infinite series today. What are we doing? We got a couple days on sequences. Oh, yeah. This is good stuff. Share a screen, grab a pen. Let's get it done. Let's see. This is my mirror. How's the hair looking today? I don't know. Could have used a little more effort. Come on, machine, wake up. Let's see. So, has it woke up? We'll try that again. Seems asleep to me. What's going on here? Check settings. Are we logged in to the right server? We are not. That's the problem. Kicked off of the good one. That's the problem. Man, sorry about that. Something going down here. We'll have it in a second. Got a feeling this is going to be it. Sequences. Don't trust your feelings. Check settings one more time. Are we logged into the right one? Yeah, we are. So, why don't you consider this? And so, I want you to write and play with this a little bit.
I can't see your screen.
No, it's dying. So, or it's coming on. I'm giving it time. I've been impatient, but while we're waiting. So let's say you take a daily dose. So this is the drugs in the bloodstream application. And I'll start writing as soon as my machine wakes up. But let's say you take a daily dose of 800 milligrams of whatever, some drug. And it's a daily dose. So you're going to do it again tomorrow, the next day, the next day. 800 milligrams. And let's say 20%. Let's say 20% remains in your system after 24 hours. So in other words, the next morning, let's see, 20% of 800, what is that, 160? So that means the next morning, when you take your 800 milligrams, you still have 160 left over from the day before. So now you have 960 on board. And so what does that look like as the future goes out? Again, that's an example of what we talked about yesterday, which is kind of a geometric sequence in the sense that, you know, it's 20% and 20% multiplied every time. So I want you to scratch paper for a minute while I get my act together here. I'm not sure what's going on. And let's see if we can kind of figure out what that would look like over time. What would that look like? How much do you, because of course the idea would be how much drugs do you have, say on day 12 or something. But blue collar it, like go a little slow, write down day one. Okay, day one, 800 milligrams. Day two, we just figured out that'd be 960. And so day three, and start playing around. And like, can you come up with a formula that does the job there? Let's see, what else could be wrong? Oh, that looks good.
I just want to mention, Doug, the link you have in my open math goes to your personal office room. So there was a group of us waiting in your office instead of in class. That's why a bunch just showed up.
That's not right. That is not right at all. I'm struggling, aren't I? I was wondering where everybody was. Why is this just spinning and spinning? I'm going to shut my iPad off. Turn it back on. We're going to try that first. So Cheyenne, did you guys say, maybe send it the wrong link? Is everybody coming over here from there? Or is it kind of like we're hanging out?
Yeah, I just thought that I would double check because I know that I've sometimes followed the wrong Zoom link and waited there for too long. So yeah, it's different from the one in the syllabus.
How did I screw that obvious thing up? I do not know.
That was smart. I just thought everyone was sleeping in since it's Wednesday.
Yeah, I was so confused.
I'm sorry about that. Gosh.
Yeah, you won't be rid of us that easy, Doug.
I wanted to have the morning off. It's beautiful out there. Go for a walk, you know, come on. Well, I'll fix that for tomorrow. Yes, I will. So for those of you that came in later, so we're playing around while I'm trying to get my act together with a drug in the bloodstream situation. So you take 800 milligrams every morning, but the next morning, 20% of whatever you had the day before is left in your bloodstream. And so we're wondering, what is that going to look like? So I want you to play around with that. And so to start with, blue collar, I mean, just say, okay, well, day one, start of the day, I got 800 milligrams in. But because you have 20% left the next morning, 20% of 800 is 160. So that means you still have 160 the next morning. And then you take your 800. And so the next morning, you now have 800 plus 160, you have 960. And then you have 20% left of that the next morning. And so what does that look like over time? What is that? I mean, that's kind of what we're looking at right here. And that's an example of a kind of a geometric sequence. So I want to see if you can make any progress with that. And I'm hopefully going to get my act together and start writing here in a second. Just tried shutting my iPad off and turning it back on. And we're going to see if that solved it, since my options are few. I'm not knowing much about computers. Bam, solved. We've got a screen. Most important thing I could ever teach you about math, in my opinion, is the ability to screw around. I can't tell you how many times I have been asked a math problem in the course of trying to learn this lovely and horrifying subject. And your first reaction is to stare at it and just think, God, I don't know what to do. And then you start wimping out, you know, and asking someone else or looking online or whatever. And it's like, just play around a little bit. Like, don't.
I think I found it. I think I found the equation for it.
I love it. Let's dive in and see. So we're going to look specifically just today at sequences. I'm going to give you a chance to answer that out loud in a second, Raymond. But sequences from yesterday, that's just the list, no addition sign, right? You got to have a plus sign in there, which we'll get to in a section or so. But today we're just looking at a sequence. And so for the drug in bloodstream, and of course, this is also interesting from the perspective of alcohol. If you were 21, you know, like you drink one beer, let's say, and then, you know, you wait whatever, an hour or something of that nature, and then you have another one. And so I don't know, I've never looked into this because I don't drink too much, but I think it's like 1 drink per hour. That sounds right. And so your body sort of gets rid of all of it after 1 hour. I mean, that's the rough number I have in my head, which is, I'm sure, wrong, but and so, you know, this applies to alcohol as well. So, you know, again, it's a question of how long do you wait? Well, we're waiting an entire day for our 800 milligrams per day, and 20%. So if I say kind of our A, like our A1, I guess I'll say amount. Again, I'm just going old school and saying, okay, day one in the morning, bam, 800. And I take, and from yesterday as a shortcut, let's think about this. From yesterday as a shortcut, what do you do for day 2? Again, I just did it out loud, but there's a better way to do it. In other words, if I say you have 20% left, you might take 20% of 800 and get 160. And then you have to add it to the 800 you just added. And now you're up to 960. And so what's a faster way to do that from yesterday? What's a faster way for percentages to work here? How do I get 960 a little bit faster?
Multiply by 1.2 instead.
Exactly, multiply by 1.2. So what I just did out loud was say something like, well, how do you get your next number? This was kind of yesterday's recursive idea. In other words, we're pretty good at going from one to the next. Even if you did it slowly, you would say, hey, the next number is found by taking the previous number, multiplying it by 20%, and then adding it to the previous number, right? But that would be better said if I have one of them plus another one of them, just taking 1.2 times whatever the previous number is. So 800 times 1.2, bam, you just get 960. Now I say 960 times 1.2, bam, I get 1152 times 1.2, I get 1382.4. Maybe we would be not worried about how we're rounding and so forth. But okay, I see the pattern. So do you see that as a geometric sequence? Because what are you doing each time? You're saying times 1.2 times 1.2 times 1.2. And so our question was, what do you do if you go way down here? In other words, if I wanted to skip up to say 17, day 17, or let's go for an entire month. After 1 month, what's happening inside my bloodstream after a month? And then ultimately, of course, N, what's the formula? What's the A of N formula? Raymond, you thought you had it. What is it?
800 times 6/5 to the n minus 1.
6/5 or 1.2 to the N minus 1, you say. And again, it depends on whether you start at sort of day 1 or day 0. But just to check to see if he's right, is that working? Yeah, when I stick a 1 in here, 1 minus 1 is 0, and 6/5 to the 0 power is 1, and so that'd be 800. So it's working. If I put a 2 in there, it ends up being 2 minus 1 is 1. It's working. He's exactly right. Perhaps you can see that now that I wrote this all out. And so that's kind of cool. We have this A of N formula now. So you can basically know any number in the sequence, either 1.2 or 6/5. Either one of those is great. So now we have our formula. And that's kind of the big takeaway for this. This formula gives us any number in the sequence we now want. And again, notice in this case, it makes no sense to add them together. Why would you add these? That makes no sense. There's a time for adding. This is not one of them. We're just listing the numbers in the sequence. So it's kind of cool that you can just jump out there and say, wow, at day 30, I'm going to throw day 30 in there, 800 times 1.2 raised to the 30 minus 1, the 29th power. Whoa, we're in deep trouble, man. We got 158,251. Seems like 158,000 milligrams might not be good. More realistically, I made it 20% just so it'd be large and you could kind of see it working. But maybe after one day that percentage would be really small, only like 1% or something really tiny like that. And so you would sort of say, oh yeah, well, it's pretty much gone, the next morning. But if you let the time go on, even at 1%, if you took it for a whole year, and notice if it was 1%, this number right here would be 1.01. And so after a whole year, let's just try that out for the fun of it. So if I say 800 times 1.01 raised to the, well, a whole year is 365 days, so it'd be raised to the 364 power 1.01 at 365 days. Notice, although that's a tiny percentage, you still end up with nearly 30,000 for the amount of milligrams that is in your bloodstream. Approximately 30K milligrams, even though it was only 1% left over. And so this is something I would assume if you're a doctor that you'd be concerned about. And that's something that I, just as a human being now in my 50s, like I don't take any medications, and I have to be on my deathbed before I do anything, because I see that kind of stuff as, your liver's got to deal with all that junk. And then you start taking every old person I know starts taking one medication for blood thinner or something like that. And then then maybe something else happens and they start taking a second one. Well, now those two interact and they don't understand very well how those two things interact with each other. And then it just goes on, pretty soon it's like, well, now my blood's thinner, but now I'm, every time I cut myself, I'm bleeding forever. Oh, well, then take this drug. And then pretty soon you're taking like 20 of these things. And I'm just thinking, not happening. I'm just going to, jokingly told my family that when I die, I want the death certificate to say consumption. He died of consumption from the 1800s. But main thing I want you to see here, of course, is just, again, that's a practical, one of you mentioned this yesterday, but that's a practical example of what a sequence actually could look like. And so again, as I often will in this class, for those of you that are new, I throw extra credits out there randomly just for your interest. And I use extra credits at the end of this class. If you ended up with like 89% and you asked me, is there anything I can do to get an A June 18th when this class is over? I'm going to say, yeah, remember all those extra credits? Did you do any of them? And I'm going to look at my grade book. And if you did some of them, and I go, yeah, there is a way. Good job. You did some of those extra credits. So one of the things I'm just suddenly curious about, I hope you have some curiosity left in you, is how does this actually work with respect to, say, drinking alcohol? Just because that's a little more practical to many more people, what defines one drink? I know it's like something like one beer and then, a tinier amount of glass of wine or something like that. And, how much is left over after an hour, or just play around with that concept. What does that mean? And so, by the time you say, all right, party's over, let's go home. How much is kind of left in your bloodstream, and does that affect me if I'm driving, those kinds of things. The last thing you want to do is either hurt yourself or even worse, hurt someone else because of your stupidity. Look into that. I'm sure there's been studies already done on it, but can you connect what we're discussing with something that's very practical to very many people?
So, Doug, I actually looked into this a little bit during Calc 1 because I thought I had an invention, but medication actually looks more like a parabola. Like when you pop a pill or a drink, it doesn't hit you right away. It becomes, more effective like as it goes on. And then there's a peak and then it decreases. And so I was like, I'm going to create an app like for first responders to like do that. It's already been invented, and it's actually something that like the poison control uses, all this stuff. So I talked to a doctor about it and was like going to partner with him. He's like, you're an idiot. Like we've been using this for years. So it's pretty funny.
Yeah, that's the way things are. I had an idea for a construction calculator the same way, because people are calculating stairs and rafters and all these complicated things. And I was busy kind of playing around with the graphing calculator kind of about 20 years ago, just trying to writing little programs in it, so that, and then like whatever, 6 months later there's one for sale on the market, that does all that. But yeah, you're right. I mean, it's kind of cool to point out. I'm glad you mentioned that, Connor, but the actual graph looks something like this. Like when you take the drug, it slowly increases and then it peaks up there at some point. And that's interesting to know when that peak is, especially if you drank a beer or something like that, because that'd be sort of like the worst time to drive. And then it kind of levels out and looks something like this. And of course, if you right here decide, whatever at the 1 hour point, bam, I'm going to have another drink, then it's going to, of course, do something like this, wouldn't it? And then it's going to start leveling off again. So notice it started here, but then the next one started here because you still had a little bit left over in your system, if you will. And then it slowly picks up, probably taking you a little bit higher, a little bit more than where you were before. And so, just how that all kind of behaves is really interesting. So,
yeah, and the hospital has to like ask, like, some guy will say, I took this dangerous amount of medication, but I feel fine. And it's because they're at the beginning of that parabola. And so maybe an hour later, he's like looking really, really bad. And then we have to know the lowest part to if we can send him home, because we can't send him home at like peak danger. So you have to know that graph pretty well.
Yeah, that's right. How much time does it take before it goes down that road? Yeah, that's one of the ski patrol questions we have to ask when we come upon a patient is, are you taking any medications for that same exact reason? So anyway, it's pretty interesting. But my point, I guess the biggest thing I'd like you to take away from this is these geometric sequences, what mathematicians call geometric sequences, are the result of anything changing by a percentage. And so that's why they're a great model for money and for, drugs in the bloodstream or whatever. Now, interestingly, you can probably see from the example we just used that if I ask the question, what's the limit of AN as n goes to infinity, and I guess I'll just replace an with the equation we actually found, because that's what I mean it to be anyway. So in other words, what happens over the long term here? That's the thing. One of the things we're going to be concerned about primarily today is just, what happens over the long term? Well, what we saw happening here is, notice at day 30, it was 158,000. Like, it's just going off the chart. Like, you can graph this. I mean, it's just an equation. It's an exponential equation. You should actually recognize that from algebra as being, I mean, this is the way I always wrote it out, but the amount of something you have equals the initial amount times the kind of the rate raised to the time. And that's kind of a classic equation. So our rate here is 1.2, and the time is sort of the number of days in this case. And it's kind of very similar to the equation that we used and studied before. And you might remember E even gets involved in there a little bit with the exponential equation is continuous as it would be for a drug or something. So E would belong in here as a base, better than even 1.2. But notice in our case, this thing is just going off to infinity. In other words, there's no limit. It's divergent, we would say, in a math class. So it isn't going in that direction. But do you understand that 1.2 represents 20% growth, because it's 20% well over 1? Whereas if you went the other direction and that number was less than 1, like if it was 0.9, then that would actually represent 10% loss. Because it's kind of like, my bank account or my town or whatever, this apple tree out front of my house that the deer keep eating. It's losing 10% of its foliage every night when I go to sleep, while the deer just chow down on it. So, what's the limit of that? Well, the limit is going to be 0, because this base, this rate is, since I'm losing 10%, then that number is not 10%, it's 0.9. It's relative to 1. It's 1 minus 10%, which would be 90%. So that would be 800 times 90%, 0.9 to the n minus 1. Well, because that's less than 1, the limit of that's going to be 0. Like, you're going to have no tree at some point. It's on its way to 0. However, it won't get there unless you go to infinity. Do you understand that logic? There'll always be a tiny amount left. And that's kind of what happens out here that Connor was elaborating on. In other words, if you smoke weed or drink a beer or whatever, there's actually some left 3 days later, or 10 days later. But at some point, it's either irrelevant or hard to measure or whatever. But it stays in your bloodstream for a long time. Well, that's the idea. So in this case, these geometric sequences, their limits are either going to be infinity when that rate is more than 1, or they're going to be 0 if that rate is less than 1. So interesting. So just to reiterate one thing from yesterday, as far as where we're going with this, the future of this is when the limit of our individual sequence, when that limit is equal to 0, in other words, when the terms get smaller and smaller and smaller, not bigger and bigger and bigger, like the drug stream example, bloodstream. When that's true, then S of n, as n goes to infinity, might equal, the book would say L for a limit or whatever, but S of n might equal some number. In other words, not infinity. Might actually come up with something. So yesterday we saw at the end of the day that sequence with what was that equal to? That geometric sequence where we were multiplying by 2/3 or something like that. That actually went to 19, was it, or 16 or something like that? We kind of proved that it went to 19 or not, it was 9. It went to 9. So it was kind of, wow, that actually approached something. And so this concept needs to sink in. I want to kind of say it more than once so that you understand that. And we'll play around a little bit to kind of watch that happen today. So let me ask you this, kind of our first example. These are the, if you will, boring book problems. What is the limit of this a of n? If I say 6n minus 3 over 2n plus 8. What is the limit of that as n goes to infinity? This is something we would have tackled back in Calc 1. But this an right here, this description, this formula that tells you how to get your individual numbers, that's just contrived. It's just somebody made it up. It doesn't model anything. We're just kind of playing around with it. So it's very important to understand that's our formula. And so what does that tend to? Is it on its way to 0, or is it on its way to some number?
It's going to be 1.
Try it out.
Yeah, seconded 1.
I vote 3 because you've got a 6 over 2 with the leading terms of each of those.
Yeah, and don't forget, you can literally play with it. In other words, write out A1. I'm going to do this in Excel in just a second, but if I stick 1 in there, 6 minus 3 is 3, 2 times 1 is 2, plus 8 is 10, so the first one's 3/10. That's what it started out as. Then I move to n is 2. Slow down, like you don't have to automatically know. I love that you're all willing to conjecture. Heard 1s and 3s, and I think I heard one other answer. Put 2 in, 12 minus 3 is 9. 2 times 2 is 4, plus 2 is 12, so I get 9/12. Notice it got a little bigger. I went from 0.3 to 0.75. So the question is,
I update my position. I am behind 3 now as the answer.
fail now changes to 3. So let's go, while you're playing around with that, I'm just going to go over to Excel. That's not Excel. It's green though. And I'd very much encourage you to play with Excel. It's one of the reasons I'm showing you this, because it's such an easy place to play around with this. Let's see, am I going to be able to copy things in this world? Looks like I am. I'm sure I've played with this in this world, so how do I even type numbers in here? We have to switch screens to do this, which I don't really want to do, but this is an app on my iPad, but I don't have a I have a keyboard for this, but I haven't played with it in so long, I don't even know. Let me try that a second. I'll play with that while you're thinking about something else. Don't waste our time. Time is precious. The question is kind of why, but you don't, the amazing thing about the world in which you guys live that we're studying this is you have tools that people did not have prior in history. Like there isn't any one of these questions that you shouldn't be able to answer just because you have the ability to go get all of them. So as I showed you yesterday, if you start with a 1 and a 2 and then you grab both of them and drag them down, that kind of recognizes, well, the sequence that you set up. And so over here, I'm saying, all right, that first problem, or that my equation was this cell will be equal to, I'm going to put it in parentheses, 6 times n minus 3. So that'd be 6. And in Excel, you actually have to type times. You can't just say 6n. Well, in our case, n is, well, in C4. I can just click that. 6 times C4 minus 3, close parentheses, divided by the bottom, which was 2 times n plus 8. So 2 times n, which for us is that number over there, add 8 to it, bam. And so we have our first answer, 0.3, 3/10. And so that's awesome. And now all I have to do is copy that down. And so, yeah, sure enough, I got 9/12. I got the same 2 answers I got. And now I can just say, boom, drag this thing down. And so, just watch it go slowly. It went from 0.3 to 0.75 to 1.07 to 1.13. Now it's up to 2.4. The question is, is it going off to infinity? Right now, you might think, yeah, it looks like it's going off to infinity. It started out at 0.3, it's up to 2.6. But I also notice it isn't growing very fast. In other words, that's 2.61, and then it goes to 2.62. And so it isn't really growing that fast. Now I'll just grab all these and drag it way down there. And so notice I just made 400 calculations. I mean, that's just not something people had had the access to in history before. And so they had to be a lot more theoretical about this. And so notice it's still growing, but notice now down here at 4, at A402 and A403, it's 2.966 and 2.9667 and 2.9668. And so this actually might be approaching the limit. And it looks like it's 3. And of course, we love whole numbers. And so, it might be 3, but then there's also pi, right? Like pi is kind of right there in that same vicinity. And so the question is, does it make it over the top of 3? So I drag it down another, 600, and notice it doesn't seem to do that. Now it's down to 2.98. So it does seem like it's not wanting to make it over the top of 3, doesn't it? So does that mean the limit is 3? Again, we'd like it to be, because that's a nice clean number, but in the real world, like, there's nothing special about the number 3. 2.9999987 is just as much of a number as 3 is. You and I get real happy when it's exactly 3, but numbers can be anything. So it does look like it does not want to go over the top of 3, doesn't it? But from Calc 1, perhaps you have an algebraic way to think about this. So let's look at that.
So could you take the derivative and find out where the rate of change was at 0 then?
Explain that, what you're thinking there.
If you took the derivative of that and then set it equal to 0 to find out where it would stop, like growing or decreasing.
Let's see, that's a good question. If I graph that. Yeah, so the problem with this one is it appears it started at 0.3, so it's like its graph, I think, would look something like this, wouldn't it? Like at 1, it's 0.3, and then at 2, it's 0.75. And so what it appears to be doing is kind of something like this, doesn't it? Where it's up, laying against, well, 3. So if I took 3 and kind of extended it out, it actually appears that it's kind of approaching 3. Do you agree with that? Now, based on that graph, Cheyenne, why would that be difficult, what you're saying, or somebody else? She's saying, couldn't I take the derivative and set it equal to 0 to find out where the slope is 0? Because wouldn't that tell us where the peak was? Good idea.
Because there's never a peak. It's just never going to reach 3.
Yeah, if it's approaching 3 like an asymptote, then it will never flatten out. It would have to actually kind of turn around and go back down in order for us to set a derivative equal to 0. Like that point right there then would have a slope of 0. But if this just approaches 3 asymptotically, if that's a word, seems like it should be a word, doesn't it? If it approaches 3 asymptotically, then it's actually never going to have a 0 slope, and so that wouldn't work. That's a brilliant idea. I love that.
Yeah, that makes sense.
That's the heartbeat of math, is just kind of playing around with this and asking questions and wondering about things. And so it appears to be approaching a limit of 3. Well, just have to think about this from Calc 1. I mean, if we're letting n go to infinity, then would you agree that 3 and 8 really don't make any difference here? And by the way, what if that had been 800? Or this had been 3,000? Would that make any difference? Is 300,000 a big number?
It
Not
doesn't
compared to
change end
infinity.
behavior.
So those are constants, and so they make really no difference. And so you can kind of just pretend, those don't really make much difference. And so this thing really behaves like 6n over 2n. And in this case, because you have, well, n is a big number, the big number divided by itself cancels out. And so this really is on its way to 3. And so we can say, even algebraically, that the limit of this thing is 3. Maybe a better way to approach this would even be to do this. If I took 6n minus 3 over 2n plus 8, and I said, well, I can remember what you can do to fractions. You can do the same thing to the top and the bottom. So if I said, hey, I think I'll divide the top by n, and I'll divide the bottom by n. So I'm dividing by 1, so it isn't changing anything. Then doesn't that first term become 6, and then minus 3 over n, and then this one down here becomes 2 minus 8 over n. Well, what happens to 3 over n as n goes to infinity? Isn't that dude on its way to 0? 3 over a billion, pretty much nothing. 8 over a billion, pretty much nothing. Hey, this thing's on its way to 6 over 2. It's on its way to 3. So algebraically, you can actually say the limit of this is 3, and you don't need Excel to do that. Again, the danger in this theoretically is just because it looks like it's on its way to 3, a nice clean whole number, doesn't mean it is. I'm not going to answer this right now, but here's one that's, let's see, no, that's a sum question. Now we'll do that later. So that's the nature of the type of questions you're going to get in this section. They'll just ask what the limit of something is, and you can play around with it on your graphing calculator, but even better is Excel. So why don't you try this one? This is a really interesting one. Second example. We need a new color, man. It's hard to pay attention if there's not different colors. This one's really cool. What about the limit of this statement? 1 plus 6 over n to the nth power as n goes to infinity. The limit of that sequence, each term. Before you dive into this and play around with it, stare at it for a little bit. Like, let's just talk about it, and then I'm going to kind of turn you loose to think about it a little bit. But what's going to happen to that? What's going to happen to 6 over n as n gets really large?
It's going to approach 0.
That's going to approach 0. And then, of course, the n that's on the outside is going to infinity. So would you agree this kind of looks like this, the inside is on its way to 1, but then this is on its way to infinity? So it's kind of like, what's 1 to the infinity power? I would say one answer to this is 1. Like, it doesn't matter how many times you multiply 1 by itself, 1 times 1 times 1 times 1, it's still 1, right? So you might conjecture, I think it's going to be 1. Or you might say, well, 6 over n isn't quite 0 yet, so that means that's not really 1, it's 1.0000 something, and you're raising it to the infinity power. And so although 1.0001 is a small number, when you raise it to the infinity power, it's really huge. And so actually, I'm kind of lost here. I'm kind of wondering, is this on its way to 1, or is this on its way to infinity? Play around.
I just typed in 5 million for the n, and it looks like it goes to infinity.
Yeah, start playing around. So Raymond's first. You go by Ray or Raymond? Can't remember if I asked you that.
Raymond's good.
Raymond's idea, or don't type in n as 1 and 2 and 3. Like, we're going to infinity, so get after it. You might type in a few of those to start with, but ultimately we're picking n to be a huge number. So play around. I'm interested in a conjecture from you. because this one is really cool. If I had a keyboard, what do I have? Oh, I know where it is. Found you, didn't I?
Yeah, raising 1.00000006 to the 999 billionth power definitely makes a difference. I got 403.42, so I don't think it's 1.
Fascinating, isn't it?
Wait, what power did you raise it to, Cheyenne?
I put, I think 9 nines.
And
So I
what'd
got-
you get? Did you get 403.42? Is that what you said?
Yeah.
Well, I just
I had
put in
9.
like 500,000 and I got approximately the same answer, but your number seems a lot larger than mine.
Yeah, I'm getting 403.4287935 as well.
And there's like no way
Larger.
we're using the same answer, same numbers.
No, I just had 6 over my 9 nines, and then plus 1, and then I raised that whole thing to the power of 9 nines.
My guesstimate is that where it's going to top off around 403 something.
So I'm going to go into Excel now and begin to do what you are doing. So I'm going to open a new sheet because I'm lazy, and I'm going to start at the top here. 1 and 2, bam. And I'm going to take, what did we say? 1 plus 6 divided by n, except for us, n is actually d1. Got to put plus sign. Got to put equal sign in front of that. 1 plus 6 divided by d1 raised to the d1 power. Bam. So you put 1 in, you get 7. You put 2 in, you get 16. So it appears this thing is growing. So let's let it grow a little bit. Boom. So yeah, I'm getting something in the hundreds. What's going on here? 374. So the question is, and I heard some of you say something in the 400s. The question is, what's happening here? This does appear to be approaching something. So I'm up to 393, and I heard some of you were saying you're up into the 400s and so forth now. And so, I'm down at the first 1,400 terms now, approximately. So to me, it looks like it's on its way, well, maybe to 400, but maybe it doesn't even make it to 400. Remember, I would like it to make it to 400 just because 400 is a nice clean number. Does that make sense? We think of that as like a place a number should land, but is there anything magic about 400? No. What if it approaches? Look where I'm at. I'm at 398.1744.1782. Would you agree it actually looks like this really does approach a limit? It does not go off to infinity. It does not, as we would say in this section, diverge. Or in the language of my open math, it'll be does not exist. What's the limit of this? Does not exist, because it just kept going forever. It does not look like it's going to make it to 400 to me. So what are your thoughts on this now? Because I've kind of caught up to you guys.
Well, when we put in larger numbers, it made it to 403. So
Yeah. So notice I'm only putting in, like, based on where I am right now, I'm only putting in 1976. That's not a very big number, is it? And so you guys are getting your calculator out. You don't really need Excel for this, right? You don't really need to do that. You can just pick a gigantic number. And so, what is this? And so, my thought was it's not even going to make it to 400. And you're saying, no, if we stuck a larger number in than this, then we're actually getting way over that. And so, yeah, what's going on? So would you agree this one's rather mysterious? Like this is quite a little bit less obvious? Huh. So I hope you're, I don't know, enough interested in that. Enough curious that you think, wow, number one, this really does appear to approach a limit, but this is not like the last problem, because I'm not going to be able to figure out what this is nearly so easily. And so,
So something I did is I just pushed a ton of 9s and I stored it
yeah.
for one of the variables so that I could just input it easily. And it actually came out as 1, which is really weird on my calculator.
Yeah, I'm getting 1 too.
If
Yeah.
I
you
don't know
go
if
high
I
enough,
typed it
it
in
goes
wrong.
to 1.
And so, that would be based on, well, sort of my first conjecture up here. And there would be some limits to your computer's ability to handle this, right? Whatever your computer is, whether it's your graphing calculator, your computer, whatever, it's going to blow up here a little bit. So I want to show you something rather surprising about how you can tackle this question in an actually algebraic way.
Put in like 61 trillion, which is a crazy number. And then I got a number that was 3. It was like 445. So
yeah,
it's kinda weird.
is there a way?
Go ahead, Eve.
Is there another way we could write this problem so we could kind of figure it out algebraically like we did with the last problem?
It turns out,
Like we're using exponents, so could we use like log or something?
It turns out there is a way to deal with this, and it's very surprising. And this is a very, I went from what I would consider to be a fairly easy, straightforward example to a, really difficult example. And so we'll go back and do some easier ones. But you may remember from Calc 1, I barely mentioned this to you if you were in my class, but there is a rule. Whoa, that's the wrong world. There is something called L'Hopital. Here's another extra credit for you. L'Hopital, looks like L Hospital. L'Hopital's rule. And this was an application for a derivative. And so we're going to use this here. And I think one of the reasons I don't mention it much is because you didn't need it that much. And had I taught it to you much, you would have not really been able to make much use of it. But let's just stare at this statement for a little bit. If I say an equals 1 plus 6 over n to the n power, and I'm going to do exactly what Eve suggested, which is take the natural log of both sides. And the reason I'm going to do that is because I don't like that n up in the exponent. And if I take the natural log of this side, 1 plus 6 over n to the n, do you remember that that's one of the properties of logarithms, that n can kind of pop down front? And so now I'm looking at just the right side. I'm looking at n times the natural log of 1 plus 6 over n. And now I could rewrite that, since that's n to the first power, I could rewrite that as the natural log of 1 plus 6 over n divided by n, well, to the minus 1 power. I made a fraction out of it. Again, would you agree this is rather brilliant? And what L'Hopital's rule says is if you have two functions, L'Hopital, I'll write it back here. L'Hopital's rule says if you have two functions, a function of x over the function or over some other function, in other words, a fraction, that you will have exactly the same answer if you take the derivative of both of those with respect to their limits. That doesn't mean those two fractions are equal. It just means with respect to their limits, you'll have the same exact answer. And I'm not going to go into this, but there's also some qualifications to that. It doesn't work for every single fraction. Notice in this case, and I'll just say this about L'Hopital's rule. Notice in this case, I have a fraction sitting here, and I have the natural log of 1 plus 6 over n. Well, if we let n go to infinity, you remember n's going to infinity, this is becoming the natural log of 1. Do you agree with that? Because it's natural log of 1 plus a tiny number. And on the bottom, you basically have 1 over n. And so this is actually natural log of 1 is 0 and 1 over infinity is 0. This is on its way to 0 over 0. Would you agree with that? And if you remember, that's kind of what happened with slope. Remember how slope was on its way to 0 over 0 and yet it wasn't back in Calc 1? It wasn't 0 over 0. So you can't just always use L'Hopital's rule, but you can use it when your two fractions go to 0 over 0. Like this is one of the places that you can actually use it. So what I'm saying then is that we can actually take the derivative of the top of this and the derivative of the bottom of this and then reevaluate. Well, what would that be? So if we take low, I can never remember how to spell it. I'll have to look over at it. L'Hopital, little hospital. It's got a little schwa over the top of the O. L'Hopital. What's the derivative of natural log of junk?
Was
One
it
over the
1
junk.
over?
1 over the junk. Derivative of natural log of x is 1 over x. So the derivative of natural log of that parenthesis is 1 over the top of that parenthesis.
So does that natural log of an beforehand, does that not matter
It does
anymore?
matter.
Okay.
I haven't forgot that. We'll come back to that.
Okay.
Nice point. Good point, Ben. Everybody remember that. This is not equal to an anymore. This is equal to the natural log of an, so we can't ignore that. So derivatives are the derivative of natural log of junk is 1 over the junk times the derivative of the junk. Chain rule. So let's see, what's the derivative then of 1 plus 6 over n? What's the derivative of 1 plus 6 n to the negative 1? Isn't that a better way to write 6 over n as far as the derivative? So I'd say the derivative of 1 is nothing. The derivative of 6n minus 1, the derivative means take the negative 1, multiply it out front, so it's negative 6. And then you take 1 away from negative 1, so now it's negative 2. So that's actually times negative 6 over n squared. That's what the chain rule would say. Yeah. And then the derivative of the n minus 1 on the bottom would be, as we just did on the top, you'd bring the negative 1 down front multiplied by negative 1, and then that n will become negative 2. So what L'Hopital's rule says is, hey, this new function we just made, it's the same limit, it has the same limit as the original one. We were kind of lost with the original one. Looks like the answer is, I don't know, we thought 403 and then Ben thought he got it up to 445. And so now we're like totally not sure. But it does appear it approaches something. It doesn't go to 1 or to infinity. It seems to go somewhere in between. And so what the heck is going on here? So now I've got this new function thanks to L'Hopital, the derivative of the fraction. So what the heck is this thing? I got to clean this mess up a little bit. How's your algebra skills? Can you handle that ugliness? Let's see, my thought would be, I don't like negative exponents. So my thought would be, I'm going to multiply the top and the bottom by n squared so that I can get rid of all those fractions. So let's see what happens to that. This n squared would cancel with that n squared. This would cancel with that. And so now I have -6 over the top of 1 plus 6 over n over -1. Or that'd just be 6 over 1 plus 6 over n. Do you agree with that? Did I blow it? Raymond's in. Thank you. So now, my friends, now can n go to infinity and we actually get an answer?
Wait, we forgot about the natural log
No, we
on the
didn't.
other side.
I haven't forgot. But if n, and again, but it's important that you said that, Eve, because we're not done yet. So if n goes to infinity, what does our new fraction become? What happens to this guy right here?
Goes
to
to
zero.
0.
Goes to 0, so this thing is on its way to 6. Now, Eve's reaction to that was, hey, we just did this a second ago and we didn't get 6. And so, you know, what's going on? So what's really cool about what we just did is originally we said this thing was on its way to 1 to the infinity power, right? And we were confused by that. And yet when we went in and played with it, with our technology, we said, man, the answer looks to be like 400. So it wasn't 1 or infinity. Thanks to L'Hopital, we just got this to 6. But as Eve just reminded us, that it's very important, we're still have the natural log of an on the left side. And now this side is apparently just 6. That's on its way to 6. So we have let n go to infinity at this point. Well, how do we solve for an, you algebra students?
Is it e to the 6th power equals an?
That's exactly
I
right.
think.
Thanks for weighing in and thanks for that tone of voice that's like, I think this is the answer, but I'm not sure, because that's kind of hard. You're exactly right. Bam, we just found the answer. There's the limit, e to the 6th. Type in your calculator. What's e to the 6th?
403.
403.42.
Mysterious number.
And that's what you guys were all getting at. Now, we did get some answers like Ben got 445 or something. I think your machine starts to explode. You understand that? Like as you start
Yeah, maybe
typing
it was
larger
that.
numbers, like it starts to not be able to kind of keep track of the
Mm-hmm.
size of these numbers. Because what's happening, remember, in the parenthesis at the start of this problem, inside the parenthesis here, you're getting something that is getting so tiny that it's hard to write down, right? You're getting 1.00000000000 when you stick a giant number in for n. And so can the calculator keep track of that? And then of course you're raising it to a power that is just insanely large. And so can it keep track of all that? And the answer is not really, is the answer to that. And so isn't that amazing? Like this literally is the limit of this. It's e to the 6th. Now I show you that because it's cool, but I also show you that because there's a problem in your assignment that's kind of like that. And so it's kind of weird in the end as a shortcut. This is where e came from, by the way. E as a number came from an expression like this. This is why e exists. Because what we're talking about here is something that grows infinitely slow, right? Remember yesterday when we took 6% annual percentage rate and we said, let's make it monthly. And so we divided by 12. But for continuous growth, what you're doing is taking the growth rate and dividing by billions, because you're saying it doesn't grow monthly or daily or hourly or minutely or secondly. It grows continuously, which means your growth rate is infinitely small. So it's like 1 plus a tiny number now. But because it grows infinitely slow, it also grows infinitely often. And so this is where e came from, because that's how things grow in nature. That's how they grow naturally. That's why it's called the natural logarithm. That's why e is involved. And so this is where e came from, actually, is from that limit ultimately it's the same, if your teacher showed it to you, it's the same limit that we did here. It's just you don't put a 6 up there, you put a 1. 1 plus 1 over n to the nth power, and that ends up e to the 1, not e to the 6th, and so you get e. So it's a little easier to see it happen if you stick a 1 up there instead of a 6, because we got such a gigantic number in this case. So yeah, it turns out, and that's where they're brilliant. And so that's an application for derivatives that maybe would mean something to you now. By the way, we don't have to be that good at this. This class is not all about, you know, taking these limits using kind of algebraic techniques and so forth. This is a bit of an obscure problem, but it's kind of a cool one because it actually does approach a limit between 1 and infinity somewhere, and it lands in the middle of nowhere. Like we just saw, it was 403.4287935, and the decimals just keep on going. That's just as far as my calculator will show it. So it's not like these things always land on nice whole numbers. I mean, I would love it if it landed on 400, but remember, in the math world, there's nothing special about the number 400. Decimals count. So crazy example, I think. And yet it's really cool that you can actually figure it out exactly right. Try this one. This one's a little easier. 3. Forgot how I was labeling these. 3. What about this one? What is the limit of an? If an was the sine of n over n. Again, the limit, of course, as n goes to infinity. That's kind of assumed every single time. But again, stop and think about this for a second. You should be able to reason this out without even typing it in your calculator. What happens if, notice when you take the sine of n, that means n's an angle, right? What kind of numbers do you get on the unit circle when you type in the sine of a number?
Nice whole numbers like 0, 1, -1.
Yeah, 0, 1, -1. That's if you stick with the 90, 180, 270 degrees. But because it cruises around the unit circle and sine is the y coordinate of whatever point you're on the unit circle, does it make sense the biggest number y ever gets is 1? So the largest answer you ever get out of this is 1. And the smallest number you ever get is -1. And then you get all the decimals in between. You can also get 0.1 and 0.2 and 0.3. In other words, this expression right here stays between 1 and -1 all the time. Technically it'd be less than or equal to, because it makes it to 1. Whereas the bottom, of course, is off to infinity, right? So what's this limit going to be? What kind of a number am I
Is it going to be 0?
Yeah, it doesn't matter whether the top is positive or negative, because the bottom is going off to infinity. So it's going to be on its way to 0. Now, again, you can just type that in your calculator if you want to. But the weird thing about this one is it's going to bounce back and forth. So let's just take a look at this in I'll show you something else that's kind of cool. Let's see. I don't want to see that one anymore, so go away. So same as before, 1 and 2. This, and I wonder how this works in Excel. Can I just say the sine of something? Yeah, it says it returns the sine of the angle. So I say equals the sine of that number right over there divided by that number over there. Bam, there we go. So it gave us 0.841 when it was 1. So let's just drag that down a ways. So do you see it on its way to 0? At least it looks like it does. So it started out fairly big positive number, 0.8, and then it was 0.45, and then it was 0.04, and then it jumped over to negatives. Why would it jump to a negative when the number is 4? Can you reason that out from the unit circle? Where are you on the unit circle if you're at 4 radians? remember you cruise around 180 degrees to pi, and that whole time your y values are positive. But once you go past pi, now your y values are negative for the first time. So that's why it popped over to negative. Let me show you something even cooler. If I grab these first few terms here and I go insert, I think it's insert, a scatter plot. It's kind of cool. What do you notice happening there?
Starting to oscillate.
Yeah, so one of the questions your assignment asks you that's kind of interesting when you look at a graph like this is whether it approaches the limit monotonically, or and your assignment will say non-monotonically. And that this isn't super important, but it's just kind of cool to notice. This approaches zero, but it approaches it by oscillation. It's actually oscillating. Notice it starts above one, or positive, and then it goes negative, and then it goes positive, then it goes negative, then it goes positive, and it's kind of bouncing its way to zero. Does that make sense? So if I take this out further, I'll grab all of them this time. If I grab all of them and insert a scatter plot. And let's see, one of my options. So let's drag it down a little bit further. So this will now be kind of crazy looking, I think, because I have so many terms, but I should stop right there. So for this time, notice instead of just a scatter plot, I'm going to actually connect them with some points. But does that look like anything in the world to you?
That is very cool.
Very cool, isn't it?
In engineering, we just did something about like wind hitting up against a skyscraper. And it kind of like travels back and forth before it settles again.
That's exactly right. That's exactly right. Anything oscillates like this, wind's a good example, but if your car hits like a pothole, that's kind of what happens is your wheel goes bam, and then it goes and vibrates to a stop. So, if I had a ruler, I was actually just looking for one, but I don't have one that bends. I mean, if a diving board or something and I bend this side down, it's going to go and come to a stop. And of course, that's just fun and interesting. But as Connor pointed out, this is a big deal with respect to skyscrapers. I don't know if you've seen that bridge collapse from up in Washington, Galloping Gertie. What was the name of that bridge? I can't remember. Tacoma Narrows. But back in the approximately 60s, I can't remember, it started oscillating in the wind. Like the base of it was not very strong. It wasn't built very well, and wasn't built to accommodate this. And the wind started oscillating it back and forth. And instead of oscillating to a stop like we want things to do, it oscillated and got larger and larger until it finally just broke the bridge. And so in engineering, we want stuff to oscillate to a stop like that, because that means it didn't break. So that's what oscillation looks like. Let's see what happened over here. How did this converge? What the heck is going on here? Anybody know? How do I get to the top of this faster in Excel? Isn't there some kind of like page up or something of that nature that takes me to the top?
I think you can just type A1 into the bar. There you go.
I learned something today. What's this one doing? If I grab this like visually, you can see it's just getting larger and larger. But if I insert the value for this, do you see how that's monotonically approaching? This was the 6/n one a second ago. This is monotonally approaching whatever we got, 403 point something. It didn't go above 4.3 and then below, above 403 and then below 403. It just approached it monotonically from one direction. That's the idea behind that. So that's kind of cool. And this first one, didn't it do the same thing? What happened here. What was your idea is not working all of a sudden. What did I do before that I'm not doing right now? Oh, I went up here and typed A1. That's what I did. Is that right? What am I doing wrong, Connor? I typed A1 before and it took me up there, and now all of a sudden I don't know what I'm doing.
If you go to the upper left, so yeah, right there. Try typing A1 there.
So what's this one doing? So this is much more powerful. So isn't that also monotonically approaching 3? That was our first example today. So that's kind of cool. So you'll be asked some questions like that. Not a complicated idea, but it's kind of neat. The distinction, again, I'm always fascinated by mathematicians coming up with names for things because I hated that. The concept of an idea, the idea is very simple, but when you read it, you think, oh no, does this converge monotonically? And you're thinking, oh my God, that sounds so complicated. So I hate terminology for that reason, but this is kind of a cool distinction. And so the fact that a mathematician would say that deserves a name, I totally get that. It actually works fine if you're the one to name it. It doesn't work fine when math becomes a foreign language and you're kind of asked to figure it out yourself. So we would say, I guess, that this converges by oscillation to 0, or as I said in my open math, it doesn't use the word oscillation. Every person's different. It says non-monotonically. It's non-monotone. I'm not sure if I spelled oscillation right. So you're just looking for things that pop to negatives and positives and so forth. What about, while we're on that topic, let's do this one. Here's another one. What about this one? If I say an equals -1 to the n over 2n plus 5. What's that? Well, there's a lag there. What's that -1 to the n power going to do? If you put in 1 for n, and then 2, and then 3, and then 4, and then 5, and then 6, what's going to happen? What's that -1 to the n doing?
It's gonna stay as 1.
Not always going to be 1. I heard your answer, Eve, and I think Connor weighed in too. What's -1 to the 2 power?
Oh, will it rotate back between +1 and -1?
Yeah, so -1 to the second power is +1, but -1 to the third power is -1. -1 to the fourth power is back to +1. And so do you see how that's going to create a positive and a negative, and a positive and a negative? Yet it'll always just be 1, so it isn't going to change the answer to anything. So that's going to create the oscillation. Does that make sense? So it's going to have a positive and negative answer.
Then it would have to be in parentheses, right, for that to happen? Or I don't know.
If you type it in your calculator, if you don't type -1 in your calculator in parentheses, then you won't. That won't work. You're exactly right. Unfortunately, in your calculator, when you type -1 to the n, it sees 1 to the n as exponents. I'm supposed to do those before multiplication. It sees -1 as like a multiplication problem, so that's kind of annoying.
Mine is essentially a super calculator, so it just had an error.
Meanwhile, what's happening on the bottom is n goes 1, and then 2, and then 3, and then 4, and then 5. What's happening to the bottom?
I want to say this is gonna go to 0 in some sense because the top is drifting between -1 and +1, but the bottom's getting larger.
Exactly. The bottom is just getting larger and larger and larger. It starts out when n is 1 at 7, and then n is 2, it goes up to 9, and then it goes up to 11. It's just getting bigger and bigger and bigger. And so this is really similar to what just happened a second ago. Do you see what I'm saying? This is almost identical to what happened a second ago. The top is oscillating back and forth from 1 to -1. In the case of sine, though, we got all the other numbers between 1 and -1, whereas this is only 1 or -1, but the bottom is on its way to infinity. So this is going to be identical to what we just did. It's going to look really similar. So this is going to be on its way to 0. The limit of this, we would say, is 0, and it's going to get there by oscillation. Non-monotonically, it's going to get there. Let's, just because it's fun, look at that, and then we'll get out of here for the day. We'll get you out of here reasonably on time. So yeah, parentheses, just to make sure we want that raised, -1 raised to this power over here. Except I forgot the equal sign, so it doesn't know what I mean. And then we're going to divide by, and don't do this, don't type 2 times.
I don't think your screen is sharing, Doug.
Thank you. That is user error. That is 2, -1 to the C2 power raised to the 2 divided by C2 plus 5. What's wrong with what I typed? Need parentheses on the bottom. I need everything to be divided by 2n plus 5. Bam, there we go. So
Ben really wanted to say it, but he was nervous.
you're biting your tongue like, come on, man. So again, you know, what is it? Starts out at -0.14, and then it goes to +0.11, and then it jumps to negative, and then it jumps to positive. So the top is causing the positive negative thing happening. All the while, we just see the numbers getting smaller and smaller and smaller. And so again, it's cool just to visualize and be done with this. Notice this is really different. And if I, let's see, can I change this after the fact? Never remember how to do this stuff. Series options. I don't remember how to do it. Just wasting our time. It's kind of nice because that looked like two separate graphs forming. So, you know, it's sometimes better not to do the scatter plot, but to actually connect them. So it's actually jumping. It started at negative, it jumps up, but it's oscillating, coming to a stop. And so if you take differential equations with me this summer, we'll talk about how to actually model vibrations coming to a stop. And it's so powerful because it's just such a big part of our world. You know, if a tree gets hit by wind, it's going to, you know, oscillate to a stop. And so I've said before that ultimately calculus is the mathematics of motion. And so if you don't understand calculus, then trees can't wave in the wind, and mountain bike shocks can't bounce your bike to a stop. And because I do mountain bike, that's something that's a really interesting part of how mountain biking works, because you want the shock to vibrate to a stop in such a way that it doesn't go down and then come back up and then buck you off the bike. Same as in a car, when they first came out with shocks, all they were was just a giant spring, so that when you went down in the hole, there was a giant spring, but the car then would be bouncing down the road for like the next quarter of a mile while it came to a stop. And so auto folks have continuously improved that with shocks that kind of dampen, if you will, really quickly. And so in differential equations this summer, we'll talk about damping. And we will want our shock absorber in a car not to damp as slowly as this one does. Does it make sense that here we are 30 seconds later, so to speak, and this thing is still bouncing up and down? Like, we want it to come to a stop after, you know, 0.2 seconds. And so, you know, how do you control that? How do you make that kind of thing happen? So this business of things oscillating to a stop, that's kind of a very powerful visual for what we're studying right now. So all I want to do tomorrow then is just kind of play around with some more examples. And then the examples I want to look at tomorrow, though, are going to get at kind of a race. In a sense, what you have is a race between the top and the bottom. Does that make sense? A lot of these problems are fractions. And so what if the top was like an exponential equation, but the bottom was like a factorial equation? You know, who outraces who? Well, we saw yesterday that if you had an n on the top and an n squared on the bottom will outrace the top, and so it'll go to 0. But what if there's like a line on the top and a exponential on the bottom? You know, how fast do different equations grow? And that's, again, getting at the graph that we looked at the other day where we said, yeah, that thing approached 0, but it doesn't approach it fast enough to actually approach anything. So we ended up getting an area that was infinite. But if it approached more quickly, if it damped more quickly, then all of a sudden we said, yeah, well, that actually will approach a limit now, even though it goes forever, which is amazing. And so we're going to look at all the different types of functions you've studied. Let me list them real quickly, like logarithms and polynomials and exponentials and factorials and linear equations. We're going to look at all of those and watch them in Excel sort of compete with each other and see how quickly they approach infinity or approach 0, and how they outrace each other. So we can answer questions like, you know, what's the limit of, say, n factorial, which you haven't played with very much, over e to the n? You know, is that going to go to 0 because e to the n gets bigger faster than n factorial does, or is it going to go off to infinity? Do you see what I'm saying? It's kind of a race. Who's outrunning who? If the top outruns the bottom, then it's going to be on its way to infinity. If the bottom outruns the top, however, then it'll be on its way to 0. And that's what we saw here. We had 2n plus 5. Well, that's going to outrun the top, which actually goes nowhere because it just stays between 1 and -1. It never really grows. And so the bottom outran the top. So this went to 0. And I can see that happening. So again, I would really encourage you, because of where we're going with this class, to visualize all this stuff with Excel. Like, don't just kind of answer the problems. Go in there and graph the dumb thing and play around with it a little bit and watch it happening. With respect to your assignment, you have lots of tries. You have like 3 tries with every question, so you'll be able to get them right. All right. Get on out of here. I will see you tomorrow. Stay after, as always, if you want to.
All right. Thanks, Doug.
Thank you.
Thank you, Doug.
Later, my friend.
Thank you.
See you tomorrow.
Hey, Doug, I actually wanted to pick your brain about something.
Sure, go ahead.
So I was watching this documentary a while back, and it obviously wasn't like an engineering documentary or anything, because it was in Iceland, and they talked about this bridge that was built like on 2 tectonic plates or something. Like, for some reason, the bridge would, or the 2 forms of land that the bridge was set on would grow by like a centimeter every year. Have you heard about this?
I'm Google searching that right now. That does sound vaguely familiar.
I was just wondering, because they like said it so nonchalantly. They're like, oh yeah, by the way, this happens. And I was like, from an engineering standpoint, I was like, how do they have to revisit this bridge every year and like make adjustments, or how do they form this bridge? Like, what's your thought on that?
Well, I will tell you this. Share a screen really quick. Even with respect to, you know, building a bridge not on sort of 2 separate land masses that kind of move independently of each other, which of course sounds crazy. Everything expands when it's warm and contracts when it's cold. So you have to account for that in a bridge. There has to be room for that to work. And so the way they typically do it from sort of a caveman perspective is to pour, let's say here's the ground, like the bridge over the top of Medford. You know, it's like just going over the town, because they didn't want the freeway to run right through the middle of the town. So it's not going over a river. So you basically pour a concrete tower like this to get it up in the air high enough so that we can have other roads going underneath it. And then, and this is just called a post and beam structure. So you just put a whole bunch of those. In Medford, there's 100 of them. And then when you put the deck on it, you basically put the deck right here. And that can just be a piece of concrete as well, or metal, or whatever you want it to be. And they actually build it with a gap in it like that so that it can expand and contract. But of course, not so much that it can slide off. Notice right here, it's about ready to slide off. You wouldn't want to let that happen. So I know recently they actually went back and they connected this with a cable so that it couldn't go any further, if you will. So notice like that cable stopping it from going that last inch right there, and that'd be really bad if it made it that far. And then they just put a metal plate over the top of that so that the car doesn't sort of notice it. And the metal plate will have like a, you know, a rib inside it so that it can't, maybe it'll be big enough, you know, so that it can't actually slide out of there and so forth. But it literally just sits there, and that way those can kind of move back and forth. And so in the case of the bridge you're talking about, they could have designed it with enough of that, you know, like let's say a bridge has a 60-year life before it's got to be demoed. Well, 60 centimeters, if it's a centimeter a year, then you could design that to have 60 centimeters of movement, even with this old school design. Now, in that case, it's going over water, so you don't have you're not going to do it in the same way. But the same thing is true with respect to, metal. I mean, you could have a metal I-beam like this and a metal I-beam like that. And instead of welding them together, you could put like a sheath around the whole thing so that they can slide through each other, if you will. And so it can actually open up even and not be able to, bend down. So I'm making that up. I don't know. I'm just saying as an example of
No, that makes
something you
sense.
could do to make that happen. And then of course, cables, to the extent that you're using cables have flexibility in them. And so something when stretched longer could actually kind of raise up in the air. And so
I was basically, that was great. I was basically just wondering what was keeping them from going back every year and like fixing the bridge. But I guess like the way you said it, like you're right, like they could go back in 60 years and decide if they still wanted this bridge after 60 centimeters. So that makes sense.
yeah. Well, all of them get replaced. I mean, I don't know what the life is, but it's about that. Like it's in the 60, 70-year range. And so as long as it worked for that length of time, because obviously it'd be very, very difficult to go back in and kind of retrofit it.
All right. Thanks. That was really interesting.
Yeah, good question. That's really cool.
Later.
Later, friends.
I guess I had a question about the first thing you did.
Yeah.
So it says 20% remained after 24 hours of 800 milligrams.
Yep.
So that means we had 160. Does that mean that 20% of the 960 remains, or 20% of the 800 remains?
Well, 20% of the 800 for the first day, but then the next day, because you have 20% remaining, which is 160 plus the 800, then that means the next day 20% of 960 will remain. And the next day 20% of 1152 will remain, and the next day 20% of 1382 will remain. So the percentage is taken of a different amount every day because you sort of have a residual left over. Does that make sense?
Right. So our body isn't absorbing 640 each day. It's absorbing an increasing amount each day.
That's exactly right. That's exactly right. Which is why that whole concept is a little dangerous, because you are asking, you're either peeing it out or whatever, and so then it's just gone. But your body's processing it in some way, and so your liver's got to do that. And again, the 20% is an unrealistically large amount, because by the fifth day, you're now taking a double dose ultimately, and that doesn't make any sense. Like there's no way that would work. This would make more sense if it was like months, 4 months later, but even then that's unrealistic.
So when I did that, I took 60% of 800's 160, and then 60% of 960 is 192, and then I added 800 to 192. I got 992 and not 1152. What did I do wrong there?
You should be adding your 192 to 960 because 800 is gone. You're either, to get to 1152, you're either taking 800 times 1.2 times 1.2, or you're taking 800 times 20%, which is 160, and then you're adding 160 to 800 so that the next morning after you take your pill, you're at 960. Then the next day you take 20% of 960, which is, you said, is 192, and then you add the 192 to 960 because that's your new base. Then that gives you 1152. So you're not adding it to 800. So that's like the way compound interest works with money as well. It's the same principle. This is like putting $800 in the bank and then having 20% interest compounded monthly. So 1 month later, you have $960. Well, then when you take 20% of 960, you have $192, but then you add the 192 to 960 because that's what you had at the end of that month. Does that make sense?
Right. So the end of the first day, before I take my pill, I have 160, and then I add an additional pill to it,
Exactly.
which puts me at 960. At then the end of the second day, before I take my pill, I have 20% of 960 in my blood, right? And then I take another 800 pill, which would,
Yeah. No, I see what you're saying. I see what you're saying all of a sudden here. You think about that. So you're saying, did we do this wrong? Is what you're saying, right?
well, I just, I wasn't sure I was understanding it. Yeah, I just thought I'd ask.
No, it's a great question. Wonderful question. Because you've now explained yourself enough that I now get what you're saying. And I'm suddenly doubting what I did. So maybe I'm not wrong, but maybe I am. Let's see. So you're right. So you're 800. Going slow. Then I have 20. Add that to that, make it 960 times 0.2. I'm just recreating what you did to go slow here. 960 times
Right.
2, double checking, you get 192. And then you add 800 to that. I'm thinking you're right. I'm thinking you're exactly right about this. Is this what you're getting based on your thinking?
Yeah, and it kept getting closer and closer to 1,000. I didn't go very far with it because then we started going into it, but
Yeah. So what was I thinking about that that's not true?
I think what we did was we added 960 and then we added more each day. We weren't assuming that we were only adding 800 each day.
You're saying what I was doing is kind of like the first day I took an 800 milligram pill, and the second day I took a 960 milligram pill, and then I took a 1152 milligram pill. Yeah, you're exactly right. That's one of the reasons why I encourage you guys to like blurt out a conjecture, even if you're wrong. Like even if you're wrong, because I would like to have fixed this on the fly with everybody. I'll say something about it in the morning, but I would like to have fixed that on the fly. And it's fun to think. And so even if, if I'm wrong, fine, we'll fix it. If you're wrong, fine, we'll discuss why, but at least you're on board. You know what I mean? Because if I say something and, most of the time, of course, I'm going to be right because I'm the teacher, but if you don't get that, a lot of times that'll derail you and you'll just sit there thinking about it and sort of not paying any attention because you're trying to make sense of something that I just did. And that probably happened to you, right? Like you if you were thinking and you just kind of stopped listening to what I was saying and got lost in your own world. They're just kind of wondering and trying to make sense of that. And of course, to say something out loud, both because I'm the teacher and there's 20 other people in there, it's kind of like, well, I'm probably wrong. And so I want to think about this more. I don't want to just immediately blurt it out. But I want all of you to blurt those things out, even if it just gives everybody time to, it answers a question that maybe other people had, or it gives them time to kind of process, because sometimes I'll be talking too fast. So yeah, I would say that's a genuine mistake on my part. I was treating it more like, well, money. I was treating it like money.
Right.
Well, even then it was like, yeah, so no, we're gonna have to play with that in the morning because you're exactly right. This scenario is not what happens. And so you're saying it's actually on its way to 1,000, and it actually didn't go to infinity based on what would really happen.
Yeah, I wasn't confident enough
Yeah.
to say. I just assumed that I wasn't understanding, and I'm sorry
Yeah.
about that.
Yeah, no, I love that. That's great. I'm glad you said something after class because I'm actually looking at my notes now. And I'm realizing that, oh yeah, I was just kind of going off of the first thing that occurred to me, and that's totally wrong. So,
I got something kind of similar to our first question answers when I assumed that the body just absorbs 640 milligrams each day, and then it grows more, but it doesn't grow at the same rate that ours did.
mhm. Yeah, nice job. Good observation. I love it. If you don't mind, I will credit you with that, and we'll talk about it in the morning and play with that a little more. And it's interesting. It's actually I will say this was kind of bothering me, but I just didn't take the time to slow down because I made the point. I don't know if I wrote that down. I think I wrote it down and erased it, but if that rate had even been 1.01, like only 1%, then this still goes off to infinity. Does that make sense?
Yeah,
In other words, by my description, anybody that takes any medication ends up with an infinite amount of milligrams of it in their system. And that's actually that wouldn't make any sense, right?
yeah. So how you want to cover that tomorrow and see how we write because I couldn't figure out how to write an equation for it.
Yeah, exactly right. Yeah. So we'll play with that first thing in the morning and yeah, I mean if you have time, play around with it, see if you can write the equation. If you get stuck, then great, we'll get there. We'll play with
Okay,
it.
thank you.
Get there. Nice job.